It's my pleasure to talk about cosmic explosions. Sandy said that we're all children of quantum fluctuations. Well, if you only had quantum fluctuations, it would just be a bunch of helium and hydrogen gas bags, which some people are, but most of us are not. So I'll tell you what really makes us to go from quantum fluctuations to real children. Okay, so the talk has two parts. One is on gamma-ray bursts, because the Keck Observatory contributed early in this game in a rather big way. And the second half is on supernovae. And in the second half, I'll be talking of supernovae as explosions. There'll be a later talk by Alex Filipenko on a specific type of supernovae called type 1A supernovae, which have been used as cosmic yardsticks to make amazing inferences about the origin of dark energy. So that would be an application of supernovae. Okay, well, for some reason, gamma-ray bursts have captured the imagination of public. Here's an old Sky and Tell, gamma rays of doom, why you should worry about merging neutron stars. It's if you're traveling around on an airplane and you want to engage in, let's say you feel like you're talking, it's a good magazine to carry around and display it, and it's a great conversation starter, I can assure you. Okay, I don't think we really have to worry about merging neutron stars. There are many ways by which we'll die anyway, so this is not so important. But we can come back to that if we have time, or someone can ask me a question why that might be a better way to end life than other possible ways. Okay, our story starts actually in the 60s when the U.S. and then USSR signed a treaty called the Outer Space Treaty, which prohibited, amongst other things, testing of nuclear devices above ground. Okay, it's after that all the nuclear tests went underground. And it also prohibited testing nuclear devices in space, including behind the moon and so on. So no sooner was the ink dry, there's a rush to go and or do verification. So both countries built very simple satellites, hard X-ray detectors, to look for flashes of hard X-rays or gamma rays, which you would expect from a nuclear explosion. It's hard to hide that. In fact, hard gamma-ray bursts were seen, and after a little bit of excitement, I suppose, it was known that these are not of local origin. They're of celestial origin, in fact, outside the solar system. That was in about 67, and for almost 30 years, this is a major mystery. You could almost all papers on gamma-ray bursts were like, we really don't know what they are. At one time, it was considered as the first-class mystery in astronomy. So a major mission, the Compton Gamma-ray Observatory, was launched, and it carried, amongst other things, the BATSI experiment, which this is really a school bus-sized satellite, perhaps the largest civilian satellite, with 8 detectors. And these are very simple detectors. They just look for radiation, gamma-ray radiation. And let's say the radiation is coming from from the top. Then it'll light up these 4 detectors, but it won't light up the other 4. So by sort of just taking the ratios, you can know approximately where it is in the sky. About few degrees to few tenths of degrees. And what CGR, or the BATSI experiment, showed is in this coordinate system, which astronomers like to use, it's the galactic coordinate system, and in this particular case it doesn't matter because the distribution of these points in any system is the same, namely it's isotropic. That is, the chance of seeing a gamma-ray burst in this piece of the sky is no different from that piece of the sky. So the phenomena is quite easy to describe. A few times a day you will see, if your eyes were sensitive to gamma rays, a blinding flash will be brighter than the brightest star in the sky and lasts for a few seconds and then disappears. Then 12 hours later, you'll see it's in some other direction. And if you wait long enough, it comes from everywhere. Okay, well, that's That sounds very interesting. What are the choice? Where do you think it might come from? And this would occupied astronomers for almost 30 years. Okay, so here's a schematic picture of a galaxy. Here's the center of the galaxy, which Andre has discussed in fair detail yesterday. And the sun solar system is out in the boonies. We are not in a particularly spectacular place. So from our point of view, if you look towards the galactic center, you'll see lots of stars. If I look straight up, I'll see fewer stars. And in the northern sky, the Milky Way is quite apparent during summertime because you're actually seeing the plane of the galaxy. So obviously, gamma-ray bursts cannot come from our galaxy because there's a huge difference between stars inside the plane versus above, whereas the distribution of gamma-ray bursts is isotropic. Okay, so you'll be forced to start pushing this gamma-ray burst to some hypothetical corona or the crown of the galaxy where the fact I'm not located at the center but I'm offset doesn't make much difference. Except we don't have any real denizens or any astronomical objects in the crown of the galaxy, the corona. So this gave rise to a large number of papers, typically by intellectually underemployed physicists, about, these are colliding strings, weirdo things, evaporating black holes, or whatever came to their minds. The other alternative is, what is the biggest fear? The point is that I want to have gamma-ray bursts appear isotropically. So what is the biggest sphere we can think of? I talked of this somewhat artificial construct, a big sphere, but the biggest sphere is the universe, right? In that case, I'm at the center, someone else is at the center, we're all in the center, we all win in this game, right? And therefore, the alternative is that gamma-ray bursts come from the biggest sphere of all, namely the universe. Well, there's one problem. I told you these are blinding. This is not some subtle phenomena. So if I go and place a gamma-ray burst at the distant galaxy, cosmologically distant galaxy or distant galaxy, the amount of energy it has released becomes very large. Astronomers, we are used to big numbers. We can put one and have many zeros, it doesn't phase us. But having a gamma-ray burst at redshift 1 that's typically required, and knowing how much energy we measure here, really leads to a stunning amount of energy that astronomers would be were themselves nonplussed. I hate to say, but the one time we don't deal with large numbers is our paychecks. Okay, so here's the mystery that struck astronomers. Are they nearby or are they far away? If they're nearby, what are they doing in the mysterious sphere? And more or less 30 years after the discovery or recognition of gamma-ray bursts, the Keck telescope settled the mystery of gamma-ray bursts. They really do come from the universe. They really come from very large, high redshift. And in fact, they do produce a staggering amount of energy. Okay. I gave a little punchline away, but we actually had a debate in Washington in about 95 where the 3 hours just like this, you could wear these buttons and you could say the galactic, meaning in our own galaxy, the cosmological, that means that in other very distant galaxies, and if you didn't know, you could say other, which would be like Klingon spaceships with cloaking devices. That would be a other, for example. So I collected all 3 buttons. I'm always a little sharp about such things. This is a collectible, I want to say. It's a very valuable collectible. So in the 10-minute coffee break, we can negotiate. It is the only collectible left in the world, though, I have to tell you that. So, okay, so how did all this come about that we now know these are so exotic? The story starts in 96 with the launch of Beppo-Sachs. It's an Italian-Dutch mission called Beppo-Sachs, and it carried, amongst other things, gamma-ray burst detector and X-ray telescope. And what Beppo-Sachs found was after a gamma-ray burst was detected, they slewed the telescope, made an image of that piece of sky, and found hours later a fading X-ray source. So this gamma-ray burst left some glowing embers, which we now call as afterglow. And the X-ray source was then imaged at the WHT in La Palma, and it was in fact found there's a fading optical source. Great discovery by Costa et al. And Van Paradise from the Bepo-Sachs mission. Okay, so this gave a clue on how to proceed, which is you wait for a burst to happen, then you rush around, look at the optical source, and then do what we do, or Keck telescope does really well, and which is the most important thing to do, is to get a spectrum. Now, I'm not really a spectroscopist myself. Images are fine. They're just like little playthings. The real action is the spectroscopy. I have to acknowledge that. Okay, so here's the next burst happened in 970508. And I remember this burst very well. I remember many astrophysical numbers very well. But this was particularly important for two reasons. It is with this we were able to get a spectrum and establish the extragalactic nature, as well as this happens now to be at least not the year, but the month and date of my wife's birthday, so I now never forget it. Okay? So I always get it right because I know exactly what that date is. I thought she'd be appreciative of my honesty, but turns out it doesn't. Okay, so after this burst was the usual rushing around. We got a picture at Palomar, many people got elsewhere. Then the Keck telescope had, of course, been in operation, and we got a spectrum. I know you're not supposed to show spectra, and especially spectra which are not been massaged and doctored. Those are things you really never supposed to show. But that's a raw spectrum, bunch of squiggly things. But if you look in more closer, you'll find some characteristic fingerprints that, after a couple of years of training, you recognize what they are. And we are able to establish that, in fact, this comes from intergalactic gas of the sort Jason was talking about. And we now know the redshift of these events. This one particular was about 0.85. And later, when the burst faded away, we were able to get the redshift of the galaxy and show that, in fact, the highest redshift of this intergalactic gas coincides with the redshift of the galaxy, thereby establishing that gamma-ray bursts are of cosmological origin. The next one was 971214. Here it means the year 1997, December 14th. And this one, we couldn't get the spectrum of the burst itself, but when it faded away, it was a very faint galaxy. And Keck was needed because it took us almost a night of getting the spectrum of this galaxy, and the redshift was at that time very large, so much so that when you did the usual stuff, how much energy I received here times 4 pi distance square, and then you compute the total energy, and it turns out to be very staggering. In fact, so staggering that it briefly appears as though this burst, for a few tenths of a second, put out apparently as much light as the rest of the universe. It gave rise to some alarmist news release that says Big Bang 2, and I like this because this got reported in India and not far from my hometown, and as a result I got a hometown parade because they realized that I'm some famous guy. So next year when I went back, I got the whole thing, and a little school was named after me, and so on and so forth. Okay, but the best part really is this. Okay, I'm being somewhat on dangerous political grounds here. This is really Bo Derek. Okay, somewhat, let's say, scantily clad. It's a German newspaper. And somewhere here it says, Das ist extreme phenomenon, said Shri Kulkarni, which is, so here we are with Bo Derek, the Pope's guards murdered, as well as GRBs. We are really mainstream now. Okay, how do you make such staggering amount of energy that you can compete, apparently, with the rest of the universe, if only for a few seconds? Well, the most popular way to get energy in the universe is through black holes. A static black hole has a certain efficiency of over 10%. That is when the matter reaches an innermost stable orbit. At this point, whatever energy you released, gravitational energy to this point is released, and then the material gets advected, and that's it. But if you have a rotating black hole, a maximum rotating one, you can increase it by a factor of 6. So for every gram of matter you put on such a black hole, you can almost get 1 gram c square, about half gram c square. Rotating black holes, the best. That's the way we solve an energy problem in the universe. Okay, so there are two models. One is a massive neutron massive star. It's rotating a bit. You have the old analogy. There's a skater. She or he pulls the dumbbells in, as they're circling around. You pull the dumbbells in. You whip up very rapidly. In the same way, as this massive star collapses, it whips up, becomes a rapidly rotating black hole. Other one is you can have two neutron stars, they coalesce, and then obviously there's a lot of angular momentum. Okay, so you can then use these GRBs to study all sorts of stuff in between, and in this case, molecular hydrogen was seen along an intervening galaxy system. Along from the host galaxy. This work by Jason with the Elris instrument. The goal is in the long run that GRBs will be used to study the intergalactic medium, maybe even to redshift 10, as if the universe is making such objects. Okay, now let me move on to the second half of the talk, which is Supernova Explosion, is supernovae, and what we have found from Keck. Well, every time a star dies, in this case, there's a supernova here, and there's another one. This is the Whirlpool Galaxy M51. It's a prolific graveyard. Okay, stars die there rather more frequently than our own galaxy. And this is what's called a core collapse. There's basically two types of supernovae. This is a rare type, actually, the so-called 1A. And by all standards, they would be kind of a curiosity. It just turned out they're very good for cosmic yardsticks. They're not particularly important from the point of view of a supernova person, but they may be important for certain things like making iron. Anyway, and the other one is how stars die the usual way. They burn hydrogen to helium, then at some point they run out of hydrogen, then they burn helium to carbon, run out of carbon, so on and so forth, and they burn all the way to iron. It's a more stable nucleus. It stops then, and the star explodes. Okay, so all these things, the periodic table, hydrogen, helium, a little bit of lithium, that's all the universe made. It was a very boring universe. Okay? And then the real thing happened, supernovae, stars dying, and that's how you populated the rest of the periodic table, and that's how life came about. Okay, well, so in this particular case, the way the basic value of Keck has been that the discoveries are made all over. For example, at Catalina Sky Survey, Pan stars, the Berkeley Katzmann telescope at Lick, Palomar Transient Factory, and amateurs. Here I show a picture of very famous Japanese amateur who's single-handedly found 70 supernovae in his lifetime, and had a pleasure of meeting him in his hometown in Japan. So those are found elsewhere, but then you need Keck to do the spectroscopy, understand the supernovae, and what they're going to tell us from what sort they are, what are the details about it. Okay, so the project that for our group has been extremely important for the Keck work is this Palomar Transient Factory, which I gave a talk a couple months ago here. We use this as a factory where we image with this telescope, we verify with the other one, do preliminary spectroscopy here, and then the most detailed work that all happens at the Keck Observatory. Okay, the sensitive spectrograph at Keck are crucial, and because this is a machine, we can now routinely discover about a dozen supernovae a night. And if you can't sort them out, it's just a waste. It just means you've discovered a dozen supernovae a night. It's a big collaboration involving not just Caltech, but our UC colleagues and colleagues elsewhere. And it's a very large software industrial enterprise, actually, at this point. We are now approaching 2,000 spectroscopically classified supernovae, and the reason is that we can actually bang through at an alarming rate with Keck. And the fun part is here's this 4%, which are unclassified. I won't go into all these details, but the 4% means we are actually on the verge of finding new things. I'll show you a few. Okay, so here's what's sometimes called a phase space. Here's how bright supernovae are. So ignore the minus sign, but more minus means more bright, and it's in log units. And here's how long that explosion lives. Okay, so you have some things called novae, then this 1A, so they are sometimes called thermonuclear supernovae, and this core collapse. That is the one I showed you in the Messier 51, young stars dying. Well, that's sort of the phase space. This is where things happen typically. And here is the collective work, which Keck has played a large role, various observatories ranging from Catalina, Pan stars, PTF, and amateurs. And the data has come in, and now you can see that there's all sorts of supernovae. The idea that we just see a few and understood it turns out to be a rather simplistic thing. And this is not the occasion, but we are already slowly classifying. There are some which are very calcium rich, so it might be that some of these supernovae went into your teeth. There are some which we have no idea what they are. They're luminous, they're red, and they're new, luminous red novae. And there are some which theorists think had predicted, maybe we found them. And then there's a whole group that is entirely, I would say, the frontier where Keck is now working. So in this category, we now have so-called pair instability supernovae. So until, let's say 10 years ago, if you had asked some expert, even 5 years ago, oh, well, supernovae, what do you expect? Well, above 8 solar masses, that is all stars with greater than 8 solar masses, they explode as supernovae, some mostly leaving a neutron star, few cases a black hole. No, the answer is, in fact, no, so it's completely different. Yes, that's true maybe from 8 solar masses to 30, maybe 40. There are some stars which explode and leave nothing in the center. They're called as pair instability supernovae. These stars are so massive, in their interiors, the photons can collide with each other and produce electron-positron pairs. So photons are moving around rapidly. They collide, and they produce these particles which are at standstill. So suddenly the pressure has disappeared. The star implodes, and then they collide more. It implodes, and then it explodes, producing a large amount of nickel in the end. Okay, and then there are some, so this is now accepted. And Keck played a huge role in actually doing the careful abundance measurements to show that this supernova, in fact, produced many solar masses of nickel. The superluminous supernovae, this is a whole new game. I think the story is very young. They're very bright. So here's time, here's brightness, here's a 1A, which is sort of the standard bright supernova. These things are brighter at peak, they last longer, they just put out more energy. And I have to show you here, because spectra, not just one, I have to show you a whole bunch of them. Robert Quimby, who's now in Japan, he was able to show that these so-called superluminous supernovae without hydrogen, now there's a little distinction, I can't explain with hydrogen is easy to understand, without hydrogen is not easy to understand. And these are kinds of supernovae that I would say 5 years ago, if you had asked someone, they would have said, oh, we'd only see this in the early universe. We only find them locally. When I say locally, I mean redshift half at this point. So the whole how stars die is entirely the chapter is simply being written up as we go. So what's next? Well, with lots of things I talked about on this phase space. From 1 day to 1 year, we have all these phenomena, some of which we have verified, some which we expect to discover based on theory. Well, there's a huge gaping window here of below a day. In astronomy, it's like you have to be an explorer. Okay, you really have to. That's the difference between physics and astronomy. Physics, you have to put on blinders to get really work done. Astronomers, you have to think big, you have to be creative, and you have to go out there and find stuff. And that's what I think will keep us busy. And this phase space is, in fact, not empty. In fact, we found recently an object, PTF 118GG. This thing faded away in 5 hours across the night at PTF. We went to Keck, and we now have a galaxy. We spent maybe 2 nights. We don't have spectrum, but now we know what to do. MOS5 is there. We'll get a redshift. And this would, in fact, be, I think, the first of its kind, which will be a cosmological explosion without gamma rays. And it may be something called a dirty fireball or an orphan afterglow, which we don't know to sort out. Thank you. Okay, what about the future? Well, the decade of time domain astronomy is underway. Okay, that is, we got plenty of pictures of the static sky. And we got plenty of things that people are doing that use. But now taking pictures of the sky, slow movies, rapid movies, I think that's Keck spectroscopy is key. And it's not just sufficient to say, I found a supernova. That's old hat. You have to say what it is. Why is it interesting? When you find supernovae every half hour, you better know what's interesting. Spectroscopy is key. Okay, so from my perspective, the cosmic web imager that was discussed by Jason, that will be a fantastic target of opportunity machine. We want now, if you want to do these sub-day events, and if you want to go after these dirty fireballs or other such things, you want to respond rapidly. Now, this has not been our strength. Observatories like Gemini and VLT have done a very good job. But there's plenty of work to be done here, so Keck should play a role, and the deployable tertiary is important. Finally, I think this is not just the story, unlike many other things, doesn't start and end with the Keck telescope. You really need an end-to-end plan. So like you have PTF, you combine that with Keck. You have pan-stars that combine with Keck. You really need that. But the real thing which we should continue doing, which we, I think, have done a very good job, is we should continue hiring young and smart people and get rid of the old people okay. Okay, that's it. Thank you.